Good afternoon everyone, welcome to today's worked exam answer video. Today I'm having a look at an OCR A question that comes from one of the unified chemistry papers, which is the third paper that you would sit at the end of year 13. And I'm having a look at this question, which is also applicable for those of you studying AQA as well. It is thinking about enthalpy changes. We've also got the need to draw a Hess's law cycle. We're going to be using Q is MC delta T. We've got a lot of practical information, and for 6 marks we have to work out 2 different enthalpy changes, one using the Q is MC delta T equation and one from creating a cycle using Hess's law to then figure out the other enthalpy change. So in terms of my plan for this question, I'm going to go through and highlight some of the key information. I'm going to have a go at doing the question on my squared paper here. And then if anyone's got any questions, as always, you can let me know in the comments. Okay, so we've got 3 reactions here, and they want to determine the enthalpy change for this one. So Na2O is a solid reacting with hydrochloric acid, a solution, to produce sodium chloride and water. That is, I guess, the main reaction that we want to know. And it says this enthalpy change can be determined indirectly using Hess's law from the enthalpy changes of reactions 3.2 and 3.3. So we've then got these 2 reactions. They have given us for reaction 3.3 the enthalpy change already, and our goal for this question is to work out the enthalpy change for this reaction, which is where our calorimetry comes in, and then construct a cycle to be able to use these 2 values to work out the enthalpy change for the reaction across the top. So for reaction 3.2, we're weighing out a bottle containing Na2O. And we're also weighing a polystyrene cup. We're adding some water to the polystyrene cup and we're measuring its temperature. We're then going to add the solid, stir the mixture, measure the maximum temperature reached, and then we're going to weigh the empty bottle and we're going to weigh the polystyrene cup with the final solution. And then we get all of these readings. So we've got the mass readings relating to the bottle and the solid, the mass readings relating to the polystyrene cup and the final solution, and then we've got the temperature readings of the water start and end. And then helpfully it says here the density and specific heat capacity of the solution are the same as for water. Now, for those of you studying OCR, you have your specific heat capacity given to you in your data booklet. If you are an AQA student watching this, you would be given the specific heat capacity as a part of the question as 4.18 joules per Kelvin per mole. And density wise, the density of water is 1 gram per centimetre cubed. And it's really nice that we can make these assumptions, or perhaps it's not an assumption here, because therefore the mass in grams can be converted into a volume in centimetres cubed and vice versa. Okay, so the first thing that I did when I was doing this question is I started by constructing the cycle. Now that isn't necessarily how you have to start this question. It is worth 6 marks and it is one of those levelled markers where you need to pick up all of the marks in each stage in order to essentially get 5 or 6 marks for the question. Now, drawing of the cycle wasn't included until stage 3, but that doesn't mean that you have to do it in that order. They started with working out the Q is MC delta T for reaction 3.2. They worked out all of the values they would need from the data in order to work that out, and then within stage 2 it was actually getting a value for delta H for reaction 3.2. Then they went on to construct the cycle. So it doesn't necessarily matter the order in which you approach things. Obviously it's just important to make sure that you do everything you need to. So whenever I'm drawing a cycle of any kind, I would always be writing the equation that I want to know the enthalpy change for horizontally across the top of my cycle. So that's exactly what I'm doing here. Now, there are some cycles that you would be able, or be expected rather, to be able to put together using, say, formation data or combustion data. There are also instances, like in this question, where you kind of have to figure out how the cycle is going to look just by looking at the equations you've been given and trying to see, okay, well, if I start with Na2O and HCl, what might I be able to do with one of those substances by having a look at what's involved in the other equations. And that, yeah, is obviously a little bit more difficult, but what we can see is that the Na2O as a solid, we can dissolve that in water to make a solution of sodium hydroxide. So I would argue that that's going to need to be our first step, because in reaction 3.3 we're then going to be using the hydrochloric acid and our newly made sodium hydroxide, reacting those together to get the sodium chloride and the water. So in terms of my cycle, I'm going to have it so we come down here, which would then be reaction 3.2. So down here, if I'm reacting Na2O with water, which I know I don't have up here, so we would add the water in, that is going to get me 2 lots of sodium hydroxide. And then from the 2 HCl we haven't used in the first reaction and those 2 moles of sodium hydroxide, we're able to go to the products of that first reaction. Now we've got 2 HCl, 2 NaOH makes 2 NaCl, but we've only got 1 water here. But we had to, we were adding a water down here, and so I guess it's balanced. We're adding one, we're taking one away to give us the products in our reaction 1. So I can already, on my cycle, label for reaction 3.3 that the enthalpy change for that reaction is minus 57.6. Although it's not just minus 57.6, because this is per mole, and we've got HCl, NaOH, NaCl and water, whereas we have 2 NaOH plus 2 HCl making 2 NaCl and 2 water. So that value is going to need to be multiplied by 2. And obviously it's important that we remember to do that. We then are going to work out this enthalpy change here, which is reaction 3.2. So I'll just put in brackets there, and obviously I can fill that in once I've figured that out. And then we are attempting to work out this enthalpy change using our cycle. So we will then be going from the sodium oxide and the HCl to the NaOH as our intermediate, and then from the intermediate up to the products. So we're going to be following these arrows round, so we're not going to need to change any of our signs, which is nice and helpful. Now, in terms of the practical information, we can work out a few things based on this information, and again, you could do this first, or you can do it as and when you want to or need to as a part of your calculations. But let's just start by writing that Q is equal to MC delta T. In terms of the M in our Q is MC delta T, it would be the mass of whatever substance is experiencing the temperature change. So it's going to be the mass of the solution in the polystyrene cup. So M is going to be whatever the difference is between 47.33 and 21.58, which is 25.75. C is 4.18. Joules per Kelvin per mole. And then delta T we can also work out from this information. So we've got 55.5 as our maximum final temperature and 20.5 for the initial temperature. So we don't need a calculator to do that. That's going to be 35 degrees. And we can leave it in degrees because it's a temperature change. We don't need to convert both of these values to Kelvin to work out the difference, because the difference, whether it's in degrees or Kelvin, will still be 35. And then from there, I can put that in as Q equals the mass times C times my change in temperature, which gives me 3,767.225. And we need to be aware that that is going to come out in joules, and that's where it's helpful to know specific heat capacity units, joules per Kelvin per mole. Like I say, OCR students, it's in your data booklet. AQA students, you'd be given it in the question. Now, if we want to convert that into an enthalpy change, which we of course do, we then need to do our value of Q divided by moles. Now, in terms of the units of delta H, those are in kilojoules per mole. So I'm going to need to divide my current Q, which is in joules, by 1,000. And that's going to be what I put into my delta H equation. And then in terms of the moles, the thing that we can work out the moles of is the Na2O. So we've got the mass of the bottle and the Na2O solid, and then we've got the mass of the empty bottle. So again, we can figure out the difference in that to get the mass, and then we can work out the MR, and then we can work out the moles from there. So at this point, to get moles, the mass is the mass of the substance reacting. So we're going to have 16.58 take away 15.34. So the mass of the Na2O used 1.24 grams. The MR is going to be 23 twice for sodium and 16 for oxygen is 62. So therefore moles is equal to mass divided by MR. And then that is the value that I'm going to put in there for my moles. So that is 0.02. So then I can put 0.02 in there. And that gives me a value for delta H of 188. I'm just going to have a look at what significant figures have been used elsewhere. The other enthalpy change is given to 3 sig fig, so I'm going to do mine to 3 sig fig, so 188, which would then be in kilojoules per mole. However, we now need to consider whether this should be positive or negative based on, is it an endothermic reaction or is it an exothermic reaction? And when we have a look at the data, we can see that the temperature of the solution is increasing. So heat is being released to the surroundings. So this has to be an exothermic reaction. So therefore it would actually be minus 188 kilojoules per mole. And the calculator won't give you that. You're always going to have to determine for yourself whether you need to manually make your answer negative. Okay, so that is the enthalpy change for reaction 3.2. So that is what is going to be written into my cycle over here. So minus 188. And so the final thing that I need to do is work out the overall delta H value there. So that is going to be done by applying Hess's law and saying that if we can't or we don't know the enthalpy change for the direct route, we can figure it out indirectly. So we're going to be going this way round the cycle. From the reactants to the intermediate, from the intermediate to the products. Now, because my arrows of my cycle go in the same direction as the Hess's law arrows, I don't need to change the sign of my numbers. So it's going to be minus 188 add minus 57.6 times 2. And that is going to give me my final answer. There we go. So delta H for the overall reaction is minus 303.2 kilojoules per mole. And there you have it. So I don't think it's actually too bad a 6-mark question in terms of the calculations that you have to do. Personally, I think the hard part is constructing the cycle, recognising that the Na2O needs to be dealt with in order to generate the sodium hydroxide, so you can then have the neutralisation reaction happening underneath, what that's going to look like. And then I guess there is quite a lot of information which can make any question feel more overwhelming, but by breaking it down, focusing on reaction 3.2 first, Q is MC delta T, hopefully lots of you are happy with that, and then it's about putting those values into the cycle. So in terms of the mark scheme, stage 1 was for working out the mass of the solution, the temperature change, and the mass of the Na2O. Stage 2 was for using the mass and the MR to get the moles of 0.02 and for figuring out that value is minus 188. And then stage 3 was for constructing some sort of cycle like this that then enabled you to work out minus 303.2 as your final answer. Hopefully that all makes sense, guys, but as always, please do let me know if you've got any questions, or let me know in the comments if you've got any requests for other types of questions as well. Hope you're all doing well, and hopefully I'll see you soon.